In this video, we will continue our discussion of how to compute electron configurations, but this time we're going to do ions, and then in the problem later on we'll do transition metals. The important point to remember is that if you're a transition metal, you're going to lose from the d orbital first. And if given the option, you're going to lose the outer electrons. So transition metals, you're going to lose the d electrons because they're more outer. And then after you remove the outer electrons, you're going to go for the more core electrons. Well, something like this, Na plus, is very simple because we know sodium, by its position on the periodic table, is group 1A, and the alkaline metals as an ion love to be plus 1. So sodium, by virtue of it becoming plus 1, has the same electron configuration of neon. So the electron configuration of sodium is just the same as neon. And neon, if you want to do the full electron configuration count, is going to be 1s2, 2s2, and then 2p6. Moving on, magnesium plus 2. All the alkaline earth metals like to be plus 2. Magnesium is in group 2A, an alkaline earth metal. So losing 2 electrons, it will have the same electron configuration as a neon. This is why group 1 likes to be plus 1, and the group 2 elements like to be plus 2 because they can achieve noble gas electron configuration status. Okay, how about Cl minus? Okay, same thing with this halogens. Why do the halogens love to be minus 1? When they're minus 1, they gain an electron, and here they become noble. Here, by Cl becoming Cl minus, the chloride ion, it has a full 3s orbital and 3p orbital. So the 3 orbital, energy level 3, is actually full, and we consider that very stable, very content as an element. So this ion has the same electron configuration of argon. K plus. Okay, looking at potassium in the periodic table, we realize it's group 1. And group 1 loves to be plus 1 because they give up that valence electron. It gives up that 4s1 electron, and it has a full n equals 3 energy level. It will have a full 3s2 and a full 3p orbital, and will have the same electron configuration of argon. So K plus and Cl minus are isoelectric with argon. Right, that calcium plus 2 in the next problem is also in group 2 of the periodic table. Loses 2 electrons, it becomes like argon. Okay, so these have the same electron configuration. The problem is asking for it in the ground state, so I'm not going to take the time to put all of this in the ground state. But for argon, it's going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Fe plus 2. Now here we're talking about the transition metals. So important point to realize is that you're going to first lose from the d orbital. Okay, that's considered more outer. And then you're going to lose from the inner electrons. Typically these are the s and p orbitals, the s orbital and the p orbitals. So Fe plus 2 shown here. This is Fe, 26 electrons. Fe plus 2 is going to be chromium. So chromium as an electron configuration, same electron configuration as chromium, and we can write chromium as, looking at it in the periodic table, argon, 4s2, 3d1, 3d2, 3d3, 3d4. So argon, 4s2. Okay, I'm not going to write the fully extended 1s2, 2s2, 2p6, and all that stuff for argon, but that's usually what the ground state is. Copper plus 2, again, the main point here is we're going to lose D first and then the S. So copper's right here, 29 electrons, and then losing 2, it's going to make it cobalt. So what is the electron configuration of cobalt? Okay, the electron configuration of cobalt is going to be argon, 4s2, 3d1, 2, 3, 4, 5, 6, 7, 3d7. So argon, 4s2, 3d7, which is the same electron configuration as cobalt. And finally, zinc plus 2. Anytime you're in the transition metal block or the N-1D block, zinc plus 2, we're losing the D first. So the 30 electrons of zinc, we lose 1 from the D orbital. We lose a second from the D orbital to give it plus 2 status. So zinc plus 2 will have the same electron configuration as nickel. And nickel itself has an electron configuration of argon, 4s2, 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8. So it's going to be argon 4s2, 3D8. And of course,